This is the final video to discuss the Cosmology school note. Already 2 or 3 weeks ago, when I was participating in the Cosmology school, and I want to summarize in this video with the contents in the second week, the large-scale structure, gravitational wave, and the dark matters, but very briefly and quickly. So, in the previous video about the contents in the weeks 1, we already discussed about the impulsion, CMB, and the perturbation theory about the density and the structure formation. So, first of all, I want to talk about the large-scale structure. The astrophysicists analyzed such structures of the universe towards the galaxy survey. So that's just the image. We can just count the number over the functions of the energy of the blocks. The blocks is reduces when the light coming from the other sources, but the luminosity is the absolute value. So the count number capital N greater than the some blocks threshold S can be represented by the function of the distance R. So we can find the relation between the discounting number and the blocks, and its derivatives provides some information of the image count. Also, we can define the luminosity function as a differential form of the luminosity. Then depending on the luminosity scale, it has some different behaviors. For the small luminosity, it follows the power law, but the high luminosity is almost has exponential behavior. So by using such luminosity and distance relation, we can analyze how much some specific galaxy or star exists, and we can analyze some large-scale structure. And there might be some additional relation like as a Hello mass function, and by using this relation, we can obtain the general formula for the luminosity and the distance. Also, we talk about the gravitational waves on the school. The gravitational wave can be described by the perturbations of the matrix. And due to the diffeomorphism of the general relative theory, we can choose some specific gauge, and usually we adopt the transverse and the trace TT gauges. Then the Einstein field equation in the first order gives just the wave equation, and we can obtain such the Lambranchians of the metric perturbations H minimum. With the matters, there is some source term in the right hand side. So the just linearized Einstein field equation is given by the Lambranchians of the H mu equal to the T mu. And the solutions of such a wave equations is just a plane wave. There are two polarization, A mu, and is satisfied by the trace last condition and also for the transverse. So the two polarization just are given by the H plus and the H is closed mode. And by inserting the stress energy tensor, we can obtain the solutions of the TT gauges perturbing matrix as a retarded green function form. And if the systems are given by the binary objects, then the T mu can be reduced by just the mass and the functions of the velocity. and the solutions of the perturbing metric has the sequence order with the quadruple of this binary system. The third topic was dark matters. We discussed various topics in the dark matters. First of all, why the dark matter should exist. There are some several evidence and some several properties by the observation. And we turn to the candidates of the dark matter through the several model. And we also discussed about how we can detect dark matters, especially the thermal beam scenario. And we turn to the sub-CV dark matters, relatively light dark matters, and other some specific techniques of the detection. So the dark matter is a non-relativistic matter, and there are several evidence over the many scale. In the small scale, like the galactic scale, the rotation curve argue that they are shaped dark matters. On some relatively large scale, the blood cluster, when the two galaxies merges, dark matters almost no scattering. And in the dark matter's halo, as some structure formation, and in the cosmological scale, we know that there are CMB with the beatings of the dark matter density. So by using that, we can obtain the properties of the dark matters. It should be non-baryonic and weakly interactive with the standard model particle structures, and only interacts with the gravitationals. And also the dark matter should be abundant, and to explain its observational density and stable. Its lifetime should be longer than the cosmological time, and it should be dark, almost invisible, with respect to the standard model interaction. And also dark matter provides some matter power spectrum as evidence of the cluster. It should be the seed of the density perturbations of the other baryonic matter. And the dimensionless power spectrum delta scale has a different behaviors depending on the dark matter model. So for example, the cold dark matters, it has a no suppression in a small scale, but if we assume the self-interacting dark matter as IDM or ultralight dark matter, so URDM or warm dark matter WDM, then the small scale structures are suppressed. Because the some contemporaries through the interaction tendon interrupts the growth of the small scale structure. So usually the typical dark matter scenario assume that the non-relativism and the cold dark matter in the case of the thermal scenario. In the case of the warm dark matters or the light dark matters, the velocity dispersions interrupts the density perturbation growth, so the suppression sitting in the power spectrum. Such a non-relativism and cold behaviors of the dark matters, they can be analyzed with the period theorem with the average velocity. And observations gives some 200 km per second, so order 10 to the minus 3 of the light at the speed. So it's relatively slow compared to the universe temperature, so it gives a non-relativistic behavior. And also from the blood cluster, we can know that the dark matter is almost collisionless. The cross sections of dark matter is smaller than some specific values by the measurement. Also, we know that the stable condition. And the case by the case, depending on the dark matter particle series, whether it's a bosonic or the baromeans, there is some specific mass bound. So, for example, the bosonic dark matter is satisfied by the Bode statistics, so the occupation number should be large. And if the occupation number is greater than 1, then the dark matter is described by the wave-like behavior. The corresponding to wavelength is longer than in the particle separation, and the occupation number is also larger than 1, and this condition can be reduced by the mass bound. The mass is smaller than the electron volt. For specific radius size or scale of the dwarf galaxies can be motivated by the 10 to the minus 22 very ultralight dark matter scale. But for the case of the barometric dark matter, the occupation number should be smaller than 1 due to the Pauli exclusion principle. So by using that, we can obtain the lower bound of the barometric mass as a 70 electron volt, so-called a TG bound. Also, there is some upper bounds on the particle dark matter mass. From the general relativity theory, we know that the spiral's shield radius, and from the quantum mechanics, we know the Compton wave length. And if the event horizons of this dark matter overlap is smaller than the Compton wavelength, then the dark matters cannot described by the particle, so there's upper bounds of dark matter as a Planck scale. So here's the overall mass ranges of the dark matters. In the 10 to minus 22 electron volts, there are the Lyman hypothesis to explain the measure of the power spectrum and to describe why the wave dark matter shape is smaller than 90 electron volt, and if the dark matter is a baryon, then the dark matter mass shape is greater than 70 electron volt. And for the case of the thermal Williams dark matters, there is a rebound electron volt to explain the power spectrum. If the thermal dark matter is smaller than this mass, then the dark matter becomes the one more half. So this can explain the structures. And this thermal dark matter shape is smaller than the 100 TeV as a unitarity bound. And the particle dark matter shape is smaller than the Planck mass, but the composite dark matters can be larger than this mass bound. But the Lansing constraints gives the mass bounds of the composite dark matter either 10 to the 57 electron volts. The PPH is cannot larger than this mass. So I'll return back to this dark matter to fixed lighters, but again the gravitational wave. Also we can talk about the non-linear, the secondary order of the gravitational wave, because the quadratic source contributions becomes important. So here, for example, by the averaging the thrust and intensity, we can obtain the energy density of the gravitational waves. This is given by the time derivatives of the matrix. And the second order of the matrix now becomes important, because averaging of the first orders of the relevant tensors just give 0. So the quadratic orders can provide the energy thrust tensor. So the T alpha beta is given by the averages of the partial H scale. So again, for the binary system, we know that the solutions of the TT case is a matrix, and by inserting that, we can obtain the energy scale of the gravitational wave. And the scale is extremely small, so that to obtain the gravitational wave signal, the large masses requires like the black hole models or the rotations each other. So again, the dark matters, we can obtain some specific dark matter abundance by considering the thermal wave scenario. It has some specific channel between the standard model dark matters and interactions, and by the non-equilibrium dynamics governed by the Boltzmann equation, we can analyze when these dark matters are decoupled and the abundance are fixed. So the Boltzmann equation is just given by the terms with the expansion effects and the decay and the scattering in the right-hand side here. So if we assume that the dark matters and the standard models are scattering each other and simplified versions, the chi3 and the chi4 in the right-hand side is in the equilibrium species. Then again, we can define the convening abundance for convenience, and also the new variable x equal to the mx over the t. Then the Boltzmann equations can be written by this form. So for the non-relativist case, the equilibrium abundance is given by the Boltzmann expansion factors, and we can obtain the one these dark matters breathe out. Then the abundance of dark matters can be determined, and depending on the model, mediators masses can be larger than dark matters or not. So the case by case, the abundance are quite different. But there is a real Weinberg bound. Dark matters mass should be larger than CB. If not, the near-light mediators is necessary. Also, example, the large-scale structures from the DASI, dark energy survey, with the galaxies survey, then we can obtain the structures of information, and usually they use the radiation information matrix with the likelihood function. again the gravitational wave slightly some Schwarzschild matrix around the black hole. We can do the similar process to the quantum mechanics hydrogens and atoms. So there are some specific potentials from the Schwarzschild matrix, and there are some impacts of the gravity, like this form, the potentials, there are additional angular momentum distribution, and we can separate the variables of this PDE with the radial and angular partner. So we can describe the quantum mechanics like the previous of the scalar fields around the black hole. So by using the geodesic equations around the black hole, we can insert the solutions of the CT case of the gravitational wave matrix. Then we can obtain how the light distorted over this gravitational wave space-time. So it keeps the detail here. Again, the dark matter, depending on the case by the case, like as the mediated mass, the dark matter's abundance formulas quite different, so that we can adopt the decay case of the dark matter. Also, not the thermal case. In the non-thermal case, they usually adopt some misaligned mechanism with the known initial build value. Then the dark matter abundance are determined by the initial values of the build and the symmetry breaking scale. Also keeps the large scale structures. Also the statistical techniques can be adopted for the such density perturbation. Some gravitational wave topic. Like as the practicability approaches of the gravitational wave, and then now we talk about the dark matter action. There are some several way to detect of the dark matter. The direct detection uses scattering between the dark matter and the particle, and indirect detection case they use the decays of the dark matter and the nuclei as such. The dark matter is produced by standard model colorism. And we'll focus on the direct detection of the dark matter by using the dark matter chi and the nuclear scattering. And by the dark matter's energy, the nucleus has some equal energy, so we can use the initial energies of dark matter and the binary equal energies, and there are some specific sensitive energy scale for the dark matter's mass of the 100 GeV. The threshold nuclear equal is the scale of the 100 kiloelectron volt. And such dark matter and the nuclear scattering cross sections can be decomposed by the spin dependence and the independent part, and they have some other form factors with the nuclear information. And also for the light dark matters that they use electron recoil and also the phonon from the lattice. And for the such a sub-CV dark matters, they use portal-like interactions between the visible and the hidden structures. There are several portal-like kinetic mixing, Higgs portal, oxygen portal, and neutrino portal. So maybe this is almost the final pages. So in this cosmological school, we discussed about the dark matter, gravitational and large scale structures in the second week. Even though I didn't follow all the details of this school, but the networking with another people in the same area is very great, and also some topics that I discussed myself, and maybe this can be the some of the seeds of the new we have the numbers.